Welcome, this is lecture number 14. In this lecture, we are going to talk about loop interaction in current mode control and design of average current mode control. So, in this lecture, we are going to talk about modeling of current mode control under band limited current sensing, then loop interaction in current mode control under limited current loop bandwidth, then average current mode control implementation and using MATLAB, then design of average current mode control, some design aspect and few MATLAB simulation case studies. So, first we will recollect our accurate modeling under current mode control, because in the past lecture, I think in this week 8 this week, I think in the very first lecture we talked about different accurate modeling technique under current mode control. So, one of the technique that we talk about by incorporating the current ripple information in the average current information, that means the ripple current information, and that we have already derived. We have used this method in the previous lecture, and by this averaging technique we have also discussed that how to derive the small signal model, and this is particularly how to derive the duty ratio perturbation in terms of the control voltage, control current, the inductor current, which is the average inductor current perturbation, then these two are the gain which is coming due to the perturbation of the slope. Okay? And in this technique, more accurate model, we obtain that the modulator gain is simply 1 by MCT or 1 by Vm. And what is Vm? That means the sawtooth waveform that we are using, that is sawtooth waveform, it is changing from 0 to Vm, right, and for a time period of t we are talking about, right. So, and we have also discussed about this K1, K2 term. That means, we already discussed this accurate small signal model of a current mode control, like of a DC-DC. This is a buck converter, of course, it should be a buck converter, okay, under current mode control. And we have derived Z1, Z0, Zin, all this, this is Z1 is inductor, then Z0 is this one. But in case of when we want to slow down the current loop, because we are going to talk about average current mode control, where we need to extract the information of the average current, that means we have to slow down the current loop. That is one reason. The other reason is that suppose we have a band limited current sensor, that means current bandwidth, loop bandwidth is not very high, because we do not have sufficiently high bandwidth current sensor. So, under all this consideration, it is reasonable that, in fact, we have discussed the effect due to this K1, K2 are insignificant, because the ripple effect is insignificant, and that is why we generally drop it, we ignore. But in this case, even we ignore, because since we are slowing down the current loop, the perturbation in the slope, even in the modulator gain derivation, the slope effect will be primarily dominated by the compensating RAM. So, we will simply remove this, and our compensating RAM Fm we are going to consider is simply 1 by Vm, which is a RAM signal, correct. So, this is neglected for this analysis. Okay, because we have already ignored this effect in our peak current mode control, and even if we include, the effect is not very significant depending upon your load current input voltage condition, but when we slow down the current loop, we can simply remove that effect, we can eliminate, we can neglect. Then under this current, that means when we consider a current sensor for current mode control, and if the current sensor has a finite bandwidth, because if we use a, if we take a high side current sensing circuit, that means current sense amplifier. So, every current sense amplifier has a bandwidth limit, right. So, even there are many ways of implementing current sensing current, but particularly for high frequency implementation, the bandwidth of current sensor is a big concern, because we are talking about inductor current, and if we want to extract the ripple information, then the current sensor bandwidth should be much higher than at least 10 times of the switching frequency to get this ripple information. But we may not get such high bandwidth current sensor, then we can consider a low pass filter which will behave like we have a low pass filter. If the bandwidth is high, then it will reasonably represent the traditional current mode control, but if that bandwidth is smaller, then we need to see the effect. So, this will like we are taking a very simple fast order low pass filter, where the cutoff frequency is this, and this cutoff frequency will play a significant role. How are you going to set? That means, we are going to set is a fraction, is a k times switching frequency, right. Whether k, can we take fraction or it should be integer, at what value. Okay. So, under this low pass filter, we are actually sensing what control signal is nothing but the filtered current, which is the output of the low pass filter. So, this is the block diagram of the current loop, closed current loop, and we can obtain the current loop gain simply by product of all this term in this loop, and this is the expression. So, low pass filter, it is the low pass filter LPF. Okay. So, this low pass filter, we have considered that it is a first order low pass filter, and we will consider a case study and see what happened. Now, if we go back to MATLAB, where I will first show you MATLAB simulation. Here it is the low pass filter, and we are defining this transfer function from the MATLAB code, and this is our conventional voltage controller. Here we are considering additional current controller, where initially we can take simply like a constant quantity, so that as if we are not considering any current controller. So, what we are going to set? Let us say this is the model of the converter, and that we have discussed already. Suppose the low pass filter bandwidth is 10 times of the switching frequency. Okay. So, this is in radian per second. Now, sorry, it is omega, it is in radian per second. Suppose now current loop gain, initially we are taking 1, that means the current loop transfer function is simply 1. That means, if you go to the Simulink block, this is simply shorted. That means, you can assume that this path is simply shorted, like it is like simply shorted. This can be achieved by setting this GC control transfer function to 1. Okay. So, we are simply doing that. So, this is simply 1. Okay. Next, because we are not taking any integral gain. Now, voltage controller, suppose we are putting a high kV, it is a PI controller, voltage controller we are considering. So, voltage controller we are choosing in such a way, we should get sufficient bandwidth, but it should be close to 1/10 or somewhat 1/8 of the switching frequency, because beyond that the model is not valid, that we have discussed, and the current loop bandwidth is pretty high. So, let us run this simulation and check what is the response of the system when we choose such a So, here we have given a 10 ampere load step. Okay. So, it is the initial load current was very low, I can tell you that initial load resistance was set to 5 ohm. So, 5 ohm by 1 volt, 1 volt by 5 ohm is like a 200 milliampere, right. So, it is changing from 0.2 ampere to 10.2 ampere. So, it is changing from 0.2 to 10.2, the average is 10.2. Okay. Now, what are we going to show here? First thing, in the current waveform, the blue one is the actual current, that is the sense current, actual current of the converter, and the red one is the sense current, which is after the low pass filter, and the low pass filter bandwidth is 10 times the switching frequency. If you go, you see the blue one is perfectly the triangular wave that we expect in a DC-DC converter, but the sensor, due to the sensor bandwidth limit, you cannot get the sharp edges, because high frequency harmonic terms are attenuated. As a result, it will be somewhat like a smoother one, right. So, you will get close to the current waveform, but not exactly same, and you will get the response is pretty fast, because we are getting a very high bandwidth current sensor, and it looks like transient response is as usual the current mode control, like a first order behavior that we can expect using this controller. Now, keeping the same controller, suppose if we decrease the bandwidth of the current loop, that means let us say we make it instead of 10 times, make it 5 times and see what is the impact. So, before we move forward, we want to check, that means we want to overlap the response. Suppose we want to overlap the response, okay, and now we want to use this dotted line for all dotted line. The same thing we are running again, but now we have reduced the current loop bandwidth by 50%, like it is okay. So, let us see the impact. You see they are more or less close. I mean, if we go deeper, if we take one particular cycle, you see the dotted line is further getting attenuated, because you are reducing the bandwidth further and further. As a result, it is getting attenuated, and also the low pass filter is introducing a phase lag. You see the peak valley point of the filter dotted curve is coming slightly after, somewhat after, or the peak is coming somewhat after the actual peak actually cross, right. So, that means it is introducing a phase lag as well as it is attenuating the harmonics, and we are not getting any significant deviation in the response due to this low pass filter effect. Now, we want to repeat this experiment, that means we keep, because instead of putting multiple waveform, we want to run it here, the same waveform. Now, it is the dotted line, okay, and now we want to further reduce. So, now we want to further reduce the current loop, the low pass filter bandwidth to, let us say, 2 times. Now we are using solid line, and we want to plot one over other. Let us run it. So, this is I am showing, if we now reduce the current loop bandwidth to what we did now, we have reduced, now it is the current loop bandwidth is I think it is 2 times the switching frequency, that means it is further reduced, and we want to see whether there is any effect on the transient response or not. So, the transient response is slowly getting affected, and if you take the waveform, that means you can see the solid line which further reduces, that means your bandwidth is reduced further, and your response still is not drastically affected, but yes, somewhat it is affected, okay, and this will be reflected in the undershoot of the output voltage. That means you see the output voltage, okay. So, the speed of the response will be affected, but not very drastically. It is not very there is no drastic effect, because your voltage loop bandwidth is already slow, not very high. But now, if we take this example and if we do now if we take this example and we want to further reduce and make it 1/2. So, this is with 2 times the switching frequency. Now, we are making 0.5, that means half of the switching frequency, and now we are using dot dash line, and let us run it and see, and we want to see what happens if the current loop bandwidth becomes half of the switching frequency. Now, you will see the drastic change. So, first of all, the converter the severe subharmonic instability, right, because drastic change in the bandwidth of the current loop, okay. So, that means it is not stable. So, because they start interacting, here the current loop bandwidth is half of the switching frequency, and current loop also have a, that means it is coming close to the voltage loop bandwidth, which we kept 1/10 of the 1/8 of the switching frequency. They are coming close to each other. That means they are basically different by 5 times. That means the voltage loop bandwidth is more or less smaller than 1/5 of the current loop, and that is causing this severe subharmonic problem. Okay. So, if we repeat the experiment, if we repeat the experiment, that means if we take again that means 2 times, and if we repeat, and if we want to make one like a just okay. So, you want to make, now we are taking same as the switching frequency. Okay. So, what I am trying to say, still it is unstable, because I have set the voltage loop bandwidth to be almost 1/6 of the switching frequency, 1/5 to 1/6. So, I mean it is again, so the thumb rule is that it should be, the current loop bandwidth should be at least 10 times higher than the voltage loop bandwidth. And if we do that, that means in the previous case, that means one way to get rid of this problem, if we reduce the voltage loop gain by half, that means we are reducing the proportional controller gain of the voltage loop, which was earlier 100, now we are making 50. So, we are slowing down, and by that way we are trying to stabilize, but we at the same time we should also increase the compensating ramp effect, because the subharmonic is severe here, and by doing that we can okay. So, we want to repeat it. So, that means by doing that we can ensure more or less stable behavior. We can achieve the stable periodic behavior. That means if we go to the solid line, that means what we need to do, if the current loop bandwidth is slower, we have to slow down the voltage loop bandwidth, and also we may have to the ramp, because otherwise your okay. So, now it is coming, and you can see this is a response, because what is happening we will discuss. So, this is slow down. Now, if you go to our PPT, what is happening? So, in peak current mode control we have a peak current reference, right. Now, we have a peak current reference in a traditional current mode control, right. But now, this is case 1, when the bandwidth of the current loop is very high, very high. So, the current will, sense current will look something similar to the inductor current. Now, the case 2, where you have a filter current, right. So, then the current will look something like this kind of current, right. So, something like this kind of current. So, since it is getting affected and it is getting attenuated, so this is like a second case. So, in order to, that is why we are getting instability subharmonic, because this quantity is also getting because high frequency components are getting attenuated. So, this problem is coming. So, then what we have to do, the third case, in order to stabilize it, we need to add a ramp with that. That means what we need to do, we need to, if we erase this part, we need to consider this kind of ramp. That means this is our current reference, this is our current reference, and with this is our minus MC, that is the compensating ramp, and along with that now your current ripple is coming. So, it is coming, this is coming the slope, that means, and at the same time that means we are increasing this slope to make it stable, and we are also slowing down the outer loop, that means we are closing the outer loop, right. So, now that means this is kind of loop interaction. The loop interaction can cause severe problem if the current loop bandwidth comes close to the voltage loop. Now, coming back to average current mode control. So, average current mode control, we intentionally put a low pass filter to extract the average current. That means, the average current mode control, we have to control the average value of the current. That means, this value. Question is how to extract the average value. One way, if we go back to the peak current mode control. So, peak current mode control, we have a sense resistor, equivalent sense resistor. That means, if we put a sensing resistance, suppose if we take the inductor and if we put an actual current sensor and then if we use a current sense amplifier, the current sense amplifier, this is your sense resistance. So, what is your sensing? The VSN, the sense voltage, it is nothing but RS, the gain of the current sense amplifier into your IL, right. So, that means, sorry, if I write here, it is RS because your IL is flowing through it into the gain of the current sense amplifier into your IL, and this we have represented as equivalent current sense resistance into IL, because dimensionally this quantity looks like a resistance, right. So, control voltage, it is compared and sense equivalent. So, one approach, we put a low pass filter, we have discussed. So, this is a low pass filter, and if we set the bandwidth in such a way, so that we can extract the average information from the low pass filter, and then we can give a current reference. So, this can be a reference current. For example, if you go for a battery charger, that means suppose you have a buck converter, suppose you have a buck converter and which is connected to a battery. Connected to this is a battery, and you are drawing, the battery is drawing current. So, in the buck converter, that means you have an inductor and you also have a capacitor, and that is going to your battery current. This is going to your actual battery. Okay, battery negative, positive and negative terminal. So, the inductor current, we have to maintain the average value of the inductor current is same as the average the battery current, right. So, one way, if we give the reference this I ref straight away equal to I battery, and we do not take into account this closed loop, because while charging a battery there is something called CC mode, constant current mode, constant current charging. Particularly when the battery voltage goes below some threshold voltage, then we should charge the battery using a constant current charging, and when the battery voltage goes above some threshold voltage, then we go to constant voltage charging, and then the current will slowly decrease, and beyond some threshold value of the current, we simply stop the charging process. So, if we talk about the constant current charging where there is no voltage loop, that means we are sending a current reference comment to the buck converter to make sure that this battery current is nothing but the required current. Okay. So, for example, if you go to our MATLAB model, here this is the closed outer loop. Suppose we remove the outer loop and we are putting a current reference. What is the current reference? Suppose this current reference is 1, we have an initial load resistance and the load resistance V ref by R, that means if there is no external current load. So, V ref by R is giving us the load current which is going out of the converter, but if we consider also a constant like a load step transient, then this can also be considered. So, the same thing if we apply here, if we run the simulation with this without closing the loop, and we want to see what happens with the converter output, right. So, since we have not closed the loop, so it is perfectly maintaining the current, that means current is changing from one to the other, we are closely maintaining current, but here since I have not connected, I mean there is a resistive load connected. So, that is why we cannot guarantee about regulation, because in battery case, since the converter will be connected to the battery, the output voltage of the converter will be decided by the battery terminal voltage. So, we do not have to bother about this. So, low pass filter can be used to extract this in a battery charger, and we have to decide. So, this is it should be omega L. We have to decide what is my bandwidth of the low cutoff frequency of the low pass filter. So, this is generally set 1/10 of the switching frequency in general, but in low pass filter, that means if you want to extract the current more precisely, then we need to. So, this is like your low pass filter bandwidth. Another approach, we can sense directly the current, there is no low pass filter here, but our current controller should be slow enough so that it will try to extract integrate the whole inductor current over a cycle, so that it will get the, because if you integrate the ripple, because what is takes the sense current, this is the sense current, this is subtracted from the reference current, that is V con, right. So, here what I am showing that average current mode control implementation, which I have already discussed. This is a converter that we have discussed earlier, we have multiple time discussed. This is average current mode controller. What we did, there is an outer voltage loop, and which take this is the error voltage, and this is a low pass filter in the current path that we are talking about LPF, and this is a current controller GCC that we are talking about GCC, and this is sawtooth waveform. If we put a value, then accordingly it will get updated. So, this is a modulator. So, this is like your, because this whole block is represented including this also, it is like your trailing edge PWM, right, modulator, trailing edge PWM modulator. So, one way, if you set just like a reference current, no outer loop that we have discussed now, and then either you take low bandwidth current sensor or you adjust the bandwidth here, and we want to see how does it happen, how is it going to track the current. Okay. So, let us go and check the simulation. So, what we are going to do first, now we have disconnected the loop, that means outer loop is no longer there, it is disconnected, and the current loop has no integral, because earlier we have considered the current loop, now we are putting the integral action back, because the current loop should have an integral action in order to perfectly track, right. And low pass filter, initially let us take, we will take a very low bandwidth current sensor, that means let us take, we talked about let us say 0.5, and see what happened. We have set, so what we are low bandwidth. That means now we are discussing about average current mode control, where the red one is coming is the filtered current. So, we still have not extracted the average current, because we are taking some, because it is 1/10 of the switching frequency set, right, and now there is a load step changes, okay, and you can see the output voltage is now getting regulated, because the current loop has an integral action also, though we have not connected any close outer loop, voltage loop, okay, because it is the current is trying to maintain at the desired reference value. Earlier, due to, since we have considered only proportional gain in the current loop, so the output voltage regulations was affected. So, it is kind of average current, it is important that average current is maintained or not. So, it is maintained except for this slow overshoot, it is more or less maintained. Now, I want to slow down the current loop, that means I set, let us say I take 1/10 and check the current loop, I have not made any changes in the current loop, and we will see what happened, whether is it going to respond or not. See, there is a huge overshoot, because The red one, we are trying to extract the average current. Now we are trying to extract more or less the average current. So the bandwidth is very low, but we are putting some high bandwidth in the current controller. So current controller has to be slowed down. How to slow down the current controller? So one way we can reduce the current controller, that proportional controller gain, and see whether can we see any improvement or not. Okay, so I think we will not jump directly into such a large value. So initially let us simulate and see. Okay, so this is something which is undesirable because you want to extract the average current to maintain perfectly, but the penalty you are paying at this transient when the current is suddenly getting affected, right. So one way to reduce this effect, okay, sorry, we should have this to plot, just a minute. Yeah, now on top of this we want to see, that means what we want to do, the current controller gain, we will put dotted line. We want to slow down also the integral. So one by one slowly. So we want to slowly we reduce the integral gain. Why? Because if you go to the current controller gain, so what is our current controller gain? We have taken current controller proportional plus current controller integral by S. That means we can write KCP S plus KCI by S. So if we take this particular 0, that means S will be equal to KCI by KCP. Okay, so sorry, just hold on. So I want to represent this into this form. That means if I take KCI common into 1 plus S by omega Z divided by S. And what is omega Z? It is nothing but KCI by KCP, right? Because we are dividing KCP, that means I want to reduce, I want to place this 0 because this will be ultimately going to the closed loop control. So I want to reduce, that means take it to close to the imaginary axis, so that I want to reduce the integral gain, because earlier I made like a change, I have decreased this. So I want to reduce the integral gain. So how to do that? You go to the integral gain, initially it was 50,000, I made it 5,000, and let us run it. So on top of that earlier waveform I want to draw to see what happened. So since it is slow down, so it is taking time to respond, but we want to see whether there is any effect or not. So we are able to reduce slightly, but still there is a huge overshoot here. Okay, so we need to reduce both because there is a direct effect on this. So here I think the modulator gain I have taken too small, so I need to take large. Modulator gain Vm, and I also need to reduce this quantity because this proportional term also reflect a discrete jump in the reference voltage. So that effect we want to reduce. Okay, so now here, so we want to again plot it, just a minute, we want to plot it here. This is the effect, and using solid line, sorry, on top of that we want to go to the previous case. So, here what we did, we have reduced the integral gain by 10 times and the proportional gain by 2 times, because proportional. So, I will explain why it is so and we will maintain the earlier value, and let us hold on and see what happened. So, I will just explain these two cases and tell you that, yeah. So, there are two cases, let me tell you. So, the first the solid line, where I will explain there is a solid line and dotted line. So, dotted line we can reduce the effect of the overshoot can be drastically reduced, you see the dotted line. So, what did you do here? So, we have in this case the solid case, we have taken current loop proportional gain to be 1 and current loop integral gain to be 50,000, and dotted line what we did, we can use a different color. This dotted line we took KCP to be 0.5 and KCI to be simply 5,000. That means, if you see the omega Z1 which is equal to, that means 50,000, right, it is radian per second, and here if you see omega Z2, it is simply 10,000. But one interesting point, we have also reduced KCP, because if you see this controller, when you are applying a step change, the IREF was here, suddenly there is a step change, that means it is changing from some value. So, this direct delta IREF jump, so at the time of transient, since the current cannot change immediately, so this is my error current, right. So, let us say at t equal to t0, this is at t equal to t0, okay. So, if I take IE at t equal to t0, there will be immediate jump, that means there will be KCP into that delta IREF, that jump into there, plus its steady state value. So, its earlier value, steady state value. So, this jump also have to reduce, otherwise that was causing a high overshoot. So, that is why we have to reduce this gain also. So, we have simulated these cases and we can substitute, by that way we can design this controller, okay. So, that means approach 1, we will use a low pass filter, and the bandwidth of the low pass filter, either you can use 1/10 or you can use 1/5, but you have to make sure that current controller will perfectly track the average current, okay. Slope not considered. So, the current loop gain we can simply make the product, that means GC, FM, Vin by Zin, it is there, and the low pass filter, and the low pass filter already we know, and the modulator gain is 1 by Vm. So, if we take the loop, because this is a 2 loop control, and inner loop we have this low pass filter, current controller, all this, and outer loop we have a voltage controller, right, this is a voltage controller. So, we have to make sure that, so we can derive the loop gain of the outer loop TV, and we can derive the loop gain of the inner loop, that we have discussed in the previous slide. So, this is the current loop gain, this is a voltage loop gain, and we have to make sure that the two loops are separated, because in 2 loop control the inner loop must be faster than outer loop. So, if we slow down the inner loop in average current mode control by putting a low pass filter, we need to slow down the outer loop much slower. That means, we generally set the outer loop TV bandwidth almost nearly bandwidth of 1/10 of Ti, that means 1/10 bandwidth, so that it becomes, it is perfectly stable. And if you take close, we have already discussed the loop interaction, many things can happen. So, you have to make sure the stable design. The another approach, we may not need to put a low pass filter, but we can put a current sensor gain, because this current sensor gain is coming. What is that? We know that V sense is nothing but R equivalent into IL, right. So, this you can talk about this Kc, this can be a current sense gain which has a dimension of resistance, right, because it is a voltage. So, in this case we can also derive the current loop transfer function by multiplying all this product in this path, and we can obtain this Z2 from here, V in, and we can also consider this 2 loop control structure. This is my inner loop, this is my outer loop, and again we can derive, we have already derived this current loop transfer function. We can also derive the voltage loop transfer function from this expression, and this is a current loop transfer function, voltage loop gain, and again we have to make sure that current loop is much faster than voltage loop. But here the current loop bandwidth will be limited by this controller, because we have discussed, even though we put an actual inductor current rather than sensing inductor current, where we are taking actually there will be a ramp, right. So, I think here what we will do, the ramp is there. So, waveform will look like, right, and you have a sense inductor current which will be like this, and by means of this current controller we are making sure the average value of the inductor current is my desired reference. Okay. So, in summary, we have discussed impact of band limited current sensing, loop interaction aspect, we have talked about small signal modeling and design aspect in average current mode control, and we have also considered few simulation case studies. So, with this I want to finish it here. Thank you very much.